During a test run along a long straight road, the following series of speedometer readings were obtained. Please make a plot of the following: velocity versus time, average acceleration versus time, and displacement versus time. Assume that velocity changes linearly from each point to the next. And also assume that the starting position for x is at x equals 0. In this example, we are given a table showing the speedometer readings for a test run, which we can plot as speed versus time. We would like to find the average acceleration during each 3-second interval. The average acceleration, a, is equal to the ratio of change in speed to the time interval, or delta v over delta t. If subscript 1 denotes the initial position, and subscript 2 denotes the final position, then the average acceleration is equal to v2 minus v1 over t2 minus t1. First, for the time interval 0 to 3 seconds, the average acceleration is found to be equal to 0 minus 0 divided by 3 minus 0, which is equal to 0. Similarly, for the time interval 3 to 6 seconds, the average acceleration is found to be equal to 2 minus 0 divided by 6 minus 3, which is equal to 0.667. We can similarly calculate the average acceleration for the time interval from 6 to 9 seconds, as 1.33, and 9 to 12 seconds, as 1. 12 to 15 seconds, as 1. 15 to 18 seconds, as 1.33. And finally, 18 to 21 seconds, as 0.667. In Part A, we used the given table to plot velocity versus time. And then we calculated the average acceleration for every 3-second time interval, using the shown formula. And then we plotted the average acceleration versus time. Now we will calculate the displacement, x, and make a plot of displacement versus time. Recall that speed, v, is the first derivative of x with respect to t. Therefore, x of time t2 is equal to x of time t1 plus the integral from t1 to t2 of v dt. This is equal to x of time t1 plus v at time t1 multiplied by t2 minus t1 plus 1/2 of the acceleration times the square of t2 minus t1. We start by setting the first point on the graph, x at time 0, to 0. Then x of time 3 is equal to 0 plus 0 times 3 minus 0 plus 1/2 of 0 times 3 minus 0 squared, which is equal to 0. Similarly, x of time 6 is equal to 0 plus 0 times 6 minus 3 plus 1/2 of 0.667 times 6 minus 3 squared, which is equal to 3. We can similarly calculate x of time 9, as 9. And x of time 12, as 37.5. X of time 15, as 69. x of time 18, as 111. And finally, x of time 21, as 162. The given figure shows the velocity of a runner as a function of time. The runner accelerates from the starting point for 10 seconds and runs at a constant speed of 6 meters per second for the next 60 seconds. He then reaches the finish line, 80 seconds after leaving the starting point. What is his average acceleration during the intervals from 0 to 10 seconds, and from 10 to 60 seconds? And, what is his instantaneous acceleration at t equal to 25 seconds, and at t equal to 75 seconds? In this example, we are given a graph of the speed of a runner versus time. First, we would like to find the runner's average acceleration for two different time intervals. The average acceleration A is equal to the ratio of delta V, which is change in speed, to delta t, which is the time interval. If subscript 1 denotes the initial position, and subscript 2 denotes the final position, then the average acceleration is equal to v at time t2 minus v at time t1 over t2 minus t1. For the time interval from 0 to 10 seconds, the average acceleration A is equal to 6 minus 0 over 10 minus 0, which is equal to 0.6 meters per second squared. Similarly, for the time interval from 10 seconds to 60 seconds, the average acceleration A is equal to 6 minus 6 over 60 minus 10, which is equal to 0 meters per second squared. Next, we would like to find the instantaneous acceleration at 25 seconds and 75 seconds. The instantaneous acceleration is the slope of the v versus t graph. At t equal to 25 seconds, the velocity is a horizontal straight line. That is, the velocity is constant. So A is equal to 0 meters per second squared. At t equals 75 seconds, the velocity is a straight line. But the graph has a negative slope. So the value of instantaneous acceleration A, which is the slope of the line, is equal to 0 minus 3 over 80 minus 75, which is equal to negative 0.6 meters per second squared. A golf ball starts rolling at time equals 0, along a straight line. The ball's position as a function of time is given by x at time t is equal to 6 plus 2.5 times t minus 0.0525 times t squared. What is the initial position, initial velocity, and initial acceleration? When is the velocity 0? Find the time, when the ball is at a distance of 2 meters from its starting point. The position of the golf ball is given by the shown equation, x at time t is equal to 6 plus 2.5 times t minus 0.0525 times t squared. We can plot x versus t as follows. We know that velocity is the first derivative of x with respect to t, which in this case is 2.5 minus 0.105 times t, which we plot as shown. We also know that acceleration is the first derivative of velocity with respect to t, which in this case is minus 0.105. In other words, the acceleration is constant. and can be plotted as the horizontal line shown here. In part A of the solution, we need to find the initial position, initial velocity, and initial acceleration. We start by substituting t equals 0 into the displacement equation. And we get the initial position, x at time 0, is equal to 6 plus 2.5 times 0 minus 0.0525 times 0 squared, which is equal to 6 meters. Similarly for the velocity equation, we substitute 0 for t, and we get the initial velocity, v at time 0, is equal to 2.5 minus 0.105 times 0, which is equal to 2.5 meters per second. And lastly, we realize that the acceleration is constant, and is independent of time. And so a at time 0, as it is for any given time, is minus 0.105 meters per second squared. In part B, in order to find the time, when the velocity of the ball is 0, we set the velocity v, equal to 0, and solve for t. So 2.5 minus 0.105 times t, is set equal to 0. Which means that t is equal to negative 2.5 over negative 0.105. And we find that t is equal to 23.81 seconds. In part C, we want to find the time, when the ball is 2 meters from its starting point. We are given the position of the golf ball as a function of time, by the equation, x at time t, is equal to 6, plus 2.5 times t, minus 0.0525 times t squared. And we plotted x versus t. The starting point of the ball, which corresponds to time 0, is at 6 meters. Therefore the ball is 2 meters away from the starting point, at either x equals 8 meters, or x equals 4 meters. First let's consider the case when x is equal to 8 meters. Setting the value of x, equal to 8 meters, in the displacement equation, and solving for the value of t. We have the equation 8 is equal to 6 plus 2.5 times t, minus 0.0525 times t squared, which can be rewritten as 0.0525 times t squared, minus 2.5 times t, plus 2, equals 0. Notice that this is a quadratic equation, a times t squared plus b times t plus c equals 0. Where a is 0.0525, b is minus 2.5, and c is positive 2. Solving the quadratic equation for t, we get the two roots. T equals 46.81. And t equals 0.814. Next let's consider the case when x is equal to 4 meters. Setting the value of x, equal to 4 meters, in the displacement equation, and solving for the value of t. We have the equation 4 is equal to 6 plus 2.5 times t, minus 0.0525 times t squared, which can be rewritten as 0.0525 times t squared, minus 2.5 times t, minus 2, equals 0. Again, this is a quadratic equation, where a is 0.0525, b is minus 2.5, and c is negative 2. Solving the quadratic equation for t, we get two roots. T equals 48.41. And t equals negative 0.787. We will only consider the positive root, since we aren't allowing time to go negative. So in summary, the ball is 2 meters away at time t equals 0.814. 46.81 and 48.41.